Hello,
We're all looking
dearies.
for the
Welcome
signal.
to what? It was
That
there. It
signal.
was happening.
Everyone was doing this.
Wait, can I do
Looking for this.
Can I do my intro? Do
Yeah,
you want to do the intro, Matt, or should I do the intro?
you do it.
I'm doing it. Hello, dearies. Welcome to Undersampled Radio, episode 69. We have a fascinating show for you today. We have what's becoming an atypical guest on the show. We don't have a whole lot of how many sedimentologists have we had on the show, Matt?
Well, Brian Romans, Chris Jackson, me, lol. Yeah, I can't think of any more. So maybe just two, and well, 1.5. I don't know. Chris kind of seems.
You've had Zoltan on your show.
That's true.
Zoltan, yeah, good one.
Mm-hmm.
Good one, Zoltan. Yeah.
We should have an undersampled radio trivia contest. I think we would lose.
We need some data science up in here. We need
statistical
categories and we can probably predict who our next guest will be.
I like that. What's happening in Oslo?
I'm going to Oslo. I'm quite excited because, as you may know, I used to live in Norway, not in Oslo, but in Stavanger. And this is my first time back there for, basically, I left in 2000 and I've been back once to ski the Birkebeiner long distance cross country ski race thing in 2003, I think. And that's it. So I haven't been there for 15 years. Crazy. So I'm kind of looking forward to it on a cultural level. And we're teaching, Diego and I are teaching a course at Statoil to geoscientists who want to learn to code, basically. So we're teaching them Python and some little bit of machine learning stuff. It's going to be awesome.
That is awesome. I wish that I could attend.
Yeah, it would be fun to have a whole gang there. But it's going to be a pretty big class. So a little bit, it's going to be intense, but looking forward to it.
Hey, are we allowed to mention your trip down south yet?
Yeah, sure.
Okay, totally. Because I have some news about that. As of 10 minutes ago, Carl emailed me. And so I have now officially been invited to give a presentation at UT on the February 23rd about machine learning, specifically a generative deep learning problem as it relates to seismic data. So that, I think, is the week after you're giving a similar presentation at the same venue. Is that right?
Right. Well, no one's actually mentioned a presentation to me yet.
Well, you better get one ready.
Yeah, sure.
Because that's what they're expecting.
Of course, I always have several things on the go. So it's going to be an interesting trip. I'm actually coming down on the Tuesday. So I looked at the meetup.com and I saw there was a Austin Python meetup or something. So I thought maybe I'd go along to that on the Wednesday. And got a couple of, but a little bit of a loose end for a day or two. So if anyone in Austin wants to hang out or whatever, I'm up for it.
Crickets.
I'm up for whatever. And that's, there's a bit of travel coming up, actually. I've got also a course going on in Michigan, Kalamazoo.
So that's the thing you play, right?
I think.
Yeah.
I'd heard of Kalamazoo, but I'm going to go there, so that's going to be interesting. Going to hang out with some people who do gas storage exploration.
Yeah.
Rather than sort of production. And then, of course, we got APG coming up. We've put by the way, tickets are now available for the APG hackathon. Well, I shouldn't call it the APG hackathon. It isn't an APG event, but it's right before the APG. 18th to 20th of May. I guess go to agilescientific.com events and you can get tickets on Eventbrite there. We're also doing a boot camp. So and I think we're just doing 30 tickets. So it's one of the smaller versions of our hackathons. And it's probably 50% sold already. So if you're interested in coming Salt Lake City this May, then go sign up. The boot camp will be Intro to Python. The hackathon will be machine learning in geology. I'm kind of hoping we get some really good stratigraphy stuff going. So
Cool. Do you want me to help you teach the boot camp? We'd have a
that'd be amazing.
Python track or something.
I was thinking like 2 or 3 tracks. Yeah, thank you. Yeah. We got like I found this cool house. It's got like 6 bedrooms or something. So there's going to be a bit of a kind of software underground villa happening.
Oh, speaking of software underground villas, before I forget, next week on Wednesday, if you're listening to Undersampled Radio and you're on Software Underground, which is like most of our audience, we are having a meetup at the petrol station at 7 p.m. next Wednesday. So I think there's about a dozen software undergrounders coming, to Houston to hang out.
Oh, is it because of the rice? No.
It's for a few different reasons, but several of us will be in town from all over the world and the country and whatever. So it's gonna be awesome.
I saw Lucas Mossa said he was in town for the rice data science. No, it's kind of geology math thing or oil and gas math thing happening at Rice. Very cool. Okay, a bit jealous.
I have. You're welcome to come down. So I have 2 bullet points in here. I'm going to skip one because we've already said a lot of things about news. But I did want to mention one of the second bullet point I have on here because I think it's an important thing that we've touched on many times on this show, which is I have been working on quantifying and training out of gender bias in machine learning models over the past few weeks. And it's a really fascinating subject because it's the biggest of problems in machine learning. Like, we're training our models to generate the same results with the same bias that we as humans have. So racial biases, gender-specific biases, everything you can think of, human beings are training their computers to learn these biases. And fixing that problem is a very difficult problem. I would say that it is on the same order of difficulty as fixing the humans. So the reason I wanted to mention it this week is because on the 27th, my coworkers, Lynn Posick and Chris LaCava, are giving a talk about what to do about this. So how to quantify it and how to fix it. That's at a conference called Data Day Texas. It's in Austin. So if you're going to be here, check it out. If not, there'll be a video recording, and I'll link to it in the show notes so you can see it later. Okay.
Very cool. Interesting problem.
Who's our guest, Matt?
So Anjali Fernandes, who I have not met, is another Twitter sort of correspondent, I guess, acquaintance. Welcome to the show, Anjali.
Thanks for having me.
Yeah, no, I'm excited to talk to you because what really caught my eye with your Twitter feed is the awesome pictures of laboratory experiments and flume tanks and things that you post. So I really want to talk about those. But before we get to that, where are you? Where are you right now?
Physically,
which part of the world are you in? You're at UConn, is that right?
Yes, that's right. I'm at the University of Connecticut. Right now, I'm in my home, but I live in Connecticut. I work at the University of Connecticut, where I'm a sedimentologist. Yeah.
Nice. And what, how long have you been there? Are you? I get a little bit confused about all the professorial rankings in American universities.
So do we all. I've been here for now two and a half years. Yeah, that's right. 2.5 years. I'm a visiting faculty member for 2.5 years.
Oh, right, okay.
And so
Does that mean you're actually also affiliated with somewhere else? Or
no, this is my primary affiliation. I don't want there to be a record of me talking about this, so we'll leave it at that.
Fair enough.
It's not a tenure track position, and it's certainly not a tenured position. Let's put it that way.
Okay.
Yeah. So I'm here. I teach undergrads and graduate students. I am, believe it or not, the only sedimentologist in the whole University of Connecticut system. which is
okay.
Yeah.
Wow.
And
So it's your kingdom. You own sedimentology in Connecticut.
Yeah. There are enough people that I can collaborate with. So there's a few. Well, Julie Fosdick is a thermochronologist here. There are a bunch of geochemists around, a few geomorphologists. So it's all kind of in my ballpark, but not that much. So it's good. It's a good place to be.
Yeah.
And I'm very far from the very long shadow of the Jackson School, which helps.
Is that? Have you? Now, before we started the show, you mentioned that you used to live in Austin.
Yeah, I got my PhD there.
Okay, cool. And I can't remember, but you were somewhere else either before Austin or after Austin.
After Austin, I got my PhD at Austin, UT Austin, and then I moved to Tulane where I got a postdoc. I was working as a synthesis postdoc for the National Center for Earth Surface Dynamics.
Okay.
It's one of these, yeah. And after that, I moved up here.
Right.
So
right.
the only
Sorry, just because I wouldn't have known this if we hadn't just had the conversation, but Tulane is in New Orleans.
Yes, that's right. It's in New Orleans. Yes.
I realize I'm mispronouncing, but I can't quite bring myself to say New Orleans.
You don't have to until you live there. The only here, let's try this. This will be fun. The only sedimentary rocks I know about in Connecticut are pegmatites in Maine. So I don't know anything. Do you study rocks on the East Coast?
I haven't done very much in Connecticut. There's a few outcrops I can take my students to, but I've begun working a lot more in New York and Pennsylvania in the Catskills.
Cool.
But it's just getting off the ground, as all good stories begin. A paleontologist, a geochemist, and a sedimentologist went to the field. And now we're working out there. We have an NSF grant that we're working on. So, yeah. So I have to travel a bit.
Gotcha. Where's your type locality? What's your specialty, your favorite?
So I hate it when people ask me that. I do anything related to sediment, water, and rock, pretty much. So
that's cool.
in
broad arena.
Yeah, so the stuff in the Catskills is mostly dealing with landscape changes in connection to global / maybe not global cooling event that killed some of the fauna, but maybe didn't kill all of them, but elsewhere is recorded as a mass extinction event. And so there's a nice interplay with a few different things. When it comes to what I do, I also do coastal systems in terms of coastal restoration type stuff. I like to work across a few different scales. So the really short time scale is restoration. Mm-hmm. Sort of intermediate time scale is millennial scale, sedimentary trends and channel belts, especially across transitions in sediment transport regimes. So for instance, a river that's approaching an ocean, or rivers that transfer sediment to the deep marine from the shelf edge. So I like working across a few different time scales, and I work, so there's the short-term stuff obviously has a lot of field work and modeling. Longer-term stuff involves seismic interpretation, and sometimes large-scale experiments, which is the sort of stuff that I post a lot of on Twitter. Yeah, that's so cool. My type area is nowhere.
Good. Well, that's awesome. I mean, it means you get to look at a lot of different systems. That's wonderful.
Yeah, it is. It means I get to work with a bunch of different people too.
What was your PhD thesis?
It was mostly focused on deep water sedimentation. I was looking at submarine channels, actually, the mechanisms for sediment transport and different kinds of submarine channel bends, and whether they're aggradational or degradational, the types of bars that form, variable topography. And so it was seismic, fieldwork, outcrop mapping, and a bunch of really cool experiments.
Turbidites? Did you work with turbidites at all?
Yes, mostly focused on turbidites, actually.
Cool.
And did you start some physical experiments there as well? You were doing some of that?
Yeah, so I guess I first got my feet wet at UT. I worked in, David Morig was my supervisor at the time. And I don't know whether you guys have seen the deepwater sedimentary basin at UT. It was kind of the first of its kind in the States. It's like a big swimming pool, basically. So everything was on a very large scale, including mixing and shoveling of sediment. So for a while after that, I was very hesitant about working in very big tanks. Yeah, we literally had to use a crane to move a lot of stuff, and it was a lot of back-breaking labor at times. But yeah, so that's kind of where I got my feet wet, and sort of went from there. You literally, actually, feet, sometimes more.
Yeah, that's pretty cool. I've always, I've actually never visited even one of those facilities. So if the one at UT is still operational, I might try and
see
if I can get in there when I'm there next month.
Are you visiting the bureau or UTIG when you're down there?
Know.
The bureau. He's visiting the bureau.
If you're visiting the bureau, someone over there, if you just ask for Jim Buttles, someone over there will tell you how to find him, and he's the scientist that runs the lab.
Or
I'm gonna find him.
Buttles and request that he does something cool with the flume tank.
That's cool.
I'll ask him if it's he manages that whole facility.
Zoltan
I'll ask
knows
if
him.
it's a wheelbarrow day up front.
How much shoveling am I gonna have to do? You're an experienced shoveler, man. You shovel lots of snow, I imagine, so it'll be fine.
This is true.
Zoltan knows him, and Zoltan's been promising me a trip to the flume tank. I would love to wrap this all into a nice gift with a bow of us.
Wait, a gift from who to who?
Anything to do with physical experiments would be awesome. I don't do any physical experimentation anymore, and so I'm very jealous of physical modelers.
Yeah, totally. No, I mean it feels a bit like, attention-wise, has been a bit eclipsed by computer models, but computer models are quite unsatisfactory on many levels.
Yeah.
There was a remark in the show notes, Anjali, that made it sound like you'd been around that track a little bit and ended up coming back to physical modeling.
Yeah, I think all of the best problems require more than just one approach, I think. And quite frankly, all of the best scientists use more than one approach. So it's sort of it's almost iterative, right? Sometimes so if you're watching a physical experiment, you get everything's at this sort of accelerated scale. And so you're watching things happen really fast, but you're watching it over an observable spatial scale. And so you develop this intuition where it's really easy to sort of imagine in 3 dimensions what might be going on behind the outcrop, around the outcrop, on spatial scales that you can't necessarily see when you're looking at an outcrop. And at smaller scales than you would normally see if you were working with seismic data. Also, in terms of just sediment transport, sediment motion, spatial evolution of sediment transporting flows, a lot of that is still it's not resolvable, as you said, to a satisfactory scale a lot of the time with our numerical models. That's one. But also there are vast sweeping assumptions that we make very often when it comes to numerical modeling, especially when it comes to fluent sediment transport, that come down to, really fine scale assumptions that get sort of scaled up. And so they're all useful and they all have their place. And I think kind of moving back and forth between, say, a sediment transport numerical model and a physical experiment and outcrop and core and seismic, it gives you a very different kind of intuition when it comes to natural systems. And I appreciate it. Yeah.
So there's an interesting note we have in the show notes here that I am really fascinated by, having worked in the past in a physical lab and now doing all my experiments on the computer. I wonder, how do you derive quantitative results from physical models?
So, well, first of all, we don't call them physical models. We call them physical experiments. Because they're not necessarily to scale when you're dealing with flow and sediment transport, right? I mean, if everything was a one-to-one geometric scaling, we'd basically be looking at rivers transporting boulders, right? So, but how to be quantitative? It depends on the problem that you're approaching, I think. If it comes down to simple morphodynamic problems, we often use what is called dynamic scaling, where it's more about having a full range of transport styles. So if you're dealing with a flow that's able to transport sediment as both bed load and suspended load, you're covering the range of natural sediment transport styles. And that's what we would say is good enough dynamic scaling to provide realistic results. But if we're, say, dealing with whole landscapes, so if you care about, whole continental shelf margins or big deltas, often, again, it comes down to if the question that you're asking is a stratigraphic question, is it, how does stratigraphy build under a given set of boundary conditions or under a varying set of boundary conditions that are varying at a fixed rate, at different rates, excuse me. Then it actually comes down to, we can take measurements that's really all about how the topography develops through time. And so we either use laser scans or, well, indoor LiDAR, which is another kind of laser scanning, or sonar if it's subaqueous topography. But ultimately, if we have a high enough temporal resolution for the topographic scans, we're really essentially building up the landscape through time at a much finer temporal scale than you would normally be able to piece together from, say, core or outcrop or whatever. Or even looking at a river, for instance, a river or a modern delta, you won't be able to piece together that level of detail on a temporal scale that we could get from an experiment. When it comes to what we can measure, there's a whole range of stuff. If it comes to when it comes to relating surface dynamics to the stratigraphy, we can look at how quickly the channels move across the surface, what time it takes for the say, if you're dealing with delta lobes, you have different lobes of sediment stacking across your landscape. What is the time scale associated with creating a flat package built up of all these delta lobes, something that would essentially mimic your subsidence, the shape of your subsidence curve across the basin? Or what is the retention of fines in the sediment? And that we would get by either coring the deposit at the end of the experiment or cutting it, or sometimes we use color-coded sediment, where you have really fine-grained sediment. It's just a different color.
What kind of temporal scales are we talking about here?
You mean physically for the experiment, or in terms of geologic timescales?
Like if sampling rate in your upscaled version.
So if you're dealing with, all right, let's just stick to one example. If I'm, say, dealing with a delta, depending on how quickly the surface evolves, and obviously what the question is that we care about, you could, say, have a delta that is, I mean, building different delta lobes through avulsion, but it has, for each avulsion, say, maybe 100 scans. And so you have the internal stratigraphy created not only as a deposit, but as synthetic stratigraphy, which ultimately, once we sort of piece together different scans, say, you have both local erosion as well as deposition, and then you have more erosion and deposition. So you know what's missing, what's been preserved. If you have, say, an indoor LiDAR scanner or overhead photographs with color-coded sediment, you can also populate your cross-section, your stratigraphy with grain sizes. And so there's a lot of detail that you can get out of a very simple experiment. And ultimately, I mean, it's really about what the question is that you're asking, but ultimately you could simply, work through a whole parameter space of, say, varying sediment flux, water flux, sea level rise rate. Keep it really simple. If those are the three things that you're varying, and just look at how the preservation of coarse and fine varies across your delta. Look at the clustering of channels and how connected the different channels are for these different boundary conditions. And of course, the boundary conditions you choose to employ will be different based on what experiment you're planning on running. But
how much numerical modeling do you do? So like when you're incorporating, say if I'm trying to quantify the distribution of fines as a percentage of total sediment deposition, how much of that gets built into an explicit computer model? So
most of that, ideally something like this. I mean, if you're running a whole suite of experiments, we're probably talking years. So a lot of this ends up informing theory that's used to sort of make larger sweeping predictions. I know that people will often, take our whatever data that has been collected, either maybe a geostatistician or a petroleum engineer or a hydrological, anyone who really cares about reservoir trends or predictive capabilities, just based on surface dynamics, trying to be able to predict what the subsurface would look like, or the reverse problem, which would be, say, look at the subsurface and try to predict what the surface dynamics in the system look like. That question that I've spent a little bit of time thinking about primarily with geostatisticians. So just trying to ask questions like, if we have just one static image, how do we decide what the surface dynamics were, and how do we sort of develop the theory to get from just a static image, say a seismic image, where we see imprints of one transport system through time, just in one stratigraphic slice, one seismic slice. And typically a geologist will sit down and sketch out, a model of what he or she thought the system looked like through time. There'd be maybe a delta channel network and maybe an avulsion, or if it's a river, it would be a sinuous river, maybe with a splay, or maybe an avulsion, and so on. And then ultimately, we want to know how much of that information, the sketches that are being drawn, is actually giving us something realistic when it comes to building a reservoir model, right?
Yeah, quantify the uncertainty.
Exactly. And so that's where I think there's a lot of opportunity to do a lot more work with experiments, among other things. But that's one area where you guys might be particularly interested, since it involves machine learning.
We don't only do machine learning, What's the next? What's on the frontier? What's your next experiment? What are you excited about?
At the moment, I'm not running any experiments. So a lot of the most recent stuff that you've seen in terms of experiments have actually been teaching experiments, where my sedimentology and stratigraphy class will run their own experiments. So rather than me teaching them about sequence stratigraphy with 3 or 4 seismic lines or even a seismic volume, they run their whole experiment, so they know the boundary conditions, and then they cut the deposit and they look at patterns in the deposit and try to figure out which, what was preserved versus what was just, was just not there in terms of what they know of the imposed boundary conditions. So experiments-wise, I haven't done very much with that recently. In terms of research, more recently, I've been working again with a geochemist, a paleontologist, a civil engineer, and myself. We're trying to see all the best stories, right? We're trying to get an NSF grant together, and basically a whole research project together, but combining both quantitative measurements from outcrops with paleoclimate proxies and hydrological models, and sort of working through that whole loop to make predictions of paleo discharge curves, but using quantitative stratigraphy as well as some of the cutting edge hydrological models that actually will evolve channels in space and time. This is the first time anyone's tried to push it this far in terms of time. And we're doing it across a paleoclimate excursion. So we are all very much kind of at the limit of our knowledge, which is pretty exciting.
It's awesome. Forgive my ignorance. What is a paleo discharge curve?
Exactly. What is it? We are trying to get a handle on what the hydrographs associated with, you know, just different paleo channels might have looked like. And this is all, it's prediction, but the idea is to sort of go from the stratigraphy, pull out, you know, whatever components the hydrological, or rather the fluvial morphodynamics models need. And so, you know, paleo slope, channel depth, shear stress, maybe even some prediction of bed morphology or channel bend shape. Put that through this model, so inform the model, get an output, which is basically channel morphodynamics, and we're trying to get it to where it's actually building stratigraphy. So there's a portion in here where we're actually adding on a little bit to the model. And go from there and say, okay, this is the stratigraphy it generates. And this is, you know, this is the range of parameters we gave it. This is the matrix of outputs we've received. Now how to figure out whether it's giving us the stratigraphy that we've seen. And so
Sure.
That's the part where, you know, I'm kind of like working through how would we measure that? Would we measure, you know, the fraction of channelized deposits versus floodplain deposits over varying size windows or moving windows, and sort of quantify that both with the predicted stratigraphy as well as the outcrops, the percent of slack water deposits preserved within the channel versus bed load. Sorry, I'm thinking out loud here, so I'm going to stop talking.
So the outputs from this thing are a physical, like a three-dimensional array of geometries?
Of DEMs, yeah. So the hoped for outcome is going to be at a smaller than avulsion timescale. So we're not talking massive basin subsidence timescales, but the timescale associated with channel activity in one place before it jumps in and avulses to another location. But essentially with an estimated set of you know, sediment fluxes and pseudo hydrographs. So we'll make up a set of hydrographs, helped a little bit by our paleoclimate proxies. So we have a slight, more or less a decent sense of, you know, this is now where I'm definitely out of my ballpark, but basically vapor pressure deficits and so on. So we have a sense of how wet or how dry it was. And obviously, as the sedimentologist, I can look at the strata and say, we have a sense of how flashy or perennial these rivers were. Take that information, try and kick it out of the morphodynamic model, and then find a way to validate the model using the stratigraphy.
This is fascinating. This is like building the topology of an Earth system, but not just like a physical geometry topology, like a geologic record topology. This is a good question that I've been asking recently. Sort of, how do you quantify a system by its geometry? Is the word I would use, but what I mean by that is sort of like a higher dimensional setting. So if you consider things like wetness and dryness in the model as a dimension, then can you fully characterize the system by its geometric topology?
Yeah.
It's really fascinating. I mean, the way that I've been working on this problem is by using information set up in these generalized coordinate spaces, which are sometimes referred to as graphs. And you can build these really intricate and descriptive settings of your estimated properties, purely based on geometry. So I wonder if you could apply those techniques here. I think the answer is probably yes.
Probably. What sort of systems have you dealt with so far, though?
Financial transactional systems. So, like, for example...
Whoa. Okay, that was not what I was thinking of. All right, go for it. Keep talking.
Yeah. So, for example, if you have a system of entities which transact money exchanges or some other goods and services exchanges more generally.
So like a network.
Sure. Yeah, yeah. So businesses and individuals in this network. Can you characterize that system by looking at its topology? So how the money flows in between those entities? And the answer is yes. And you can discover fraudulent transactions by doing this. Similarly, you could set up a system of point locations in your geologic system, and you could have modeled or measured samples at each one of these locations. And if there's like sediment transport between the locations, you could model that as an edge in this network between these vertices and maybe make some predictions.
Yeah, so based on what you're describing, I'm immediately thinking of deltas and sort of packages of water and sediment sort of being distributed or not, stored, embezzled, whatever, held on to. Where I struggle with this, so is that network theory, by the way?
Sure. Yeah, graph theory.
Okay. Yeah. But where I struggle with this is sort of going from very physical outcrop measurements to imagining like the three-dimensional. Even so, my colleague who's the most familiar with the morphodynamic model we're planning on using. My dog is wondering why I'm talking to myself. So, a great example, right, of crossing disciplinary boundaries is only today did she realize that we don't actually have a sense of the three-dimensional shape of any one channel container, because every channel body is really a composite form, right? It's the one channel that has moved around in space and time, and so we're reconstructing what it would have looked like. And so in some cases we might potentially get a whole channel belt ridge exposed if we're really lucky, exhumed. So we have a sense of the shape of the channel, but most of the time we just have the cross section. And so it's at I think a simpler, less easy to access level than what you're describing.
Probably more complex because the problem is less posed.
Yes, less well constrained. Yeah. But yeah, it's certainly an idea.
I'm gonna stop asking stupid questions and let Matt ask you some good sedimentology questions, because I don't know anything about rocks.
I did not think that was a stupid question at all.
Matt, you're on.
Oh, that was natural. Yeah, no, I think it's interesting. I mean, I'm just sort of thinking, well, on some level, we know that these things do cluster in some high-dimensional topology, because there they are in the physical universe, clustered, like highly spatially correlated and so on. Yeah, it's just a question of, like, the thing with geology just strikes me that, and I don't know that this is, well, I'm sure it's not unique among physical sort of realms, if you like, or sciences, but it's just extremely high. It seems like it's got a very large number of parameters, and the relationships between those parameters are highly kind of nonlinear. Some of them can be switched on and off just under certain circumstances.
Yeah.
And it's one of the reasons why I think it's so interesting from a numerical modeling point of view, which is why it's fascinating to hear people like Zoltan say, well, actually, you can model sinuosity of rivers in kind of with one idea, right? He just has this sort of propagating upstream curvature, for example. And it's fascinating when simple things like that emerge. But do you like where I was just kind of interested in where these physical experiments and kind of outcrop stuff is today, like, are there any giant, are there any new physical experiment facilities being built today? Are there any big outcrops sort of based models going on? Like, and the sort of thing I have in mind as an example is where I did my PhD research was in the Pyrenees, in the Ainsa Basin. And not long after I worked there, there was a substantial experiment to go drill wells behind the outcrop, shoot seismic along the outcrop, like this massive integrated data collection effort. So it's easy to sort of read about people building new supercomputers and stuff like that. But these like physical experimentation facilities and big outcrop studies, are those still being funded in big ways? Is there anything really exciting going on right now?
So let me see. In the States, there are a few big facilities. UT is one of them. I would say the biggest and best equipped is the one up at St. Anthony Falls in Minnesota. This one is really cool because it's right below the falls, and so it basically uses the Mississippi River water to pretty much run all of the experiments, and the water gets put back into the river. So it's kind of a nice system. Although I think bottom level floods when the Mississippi floods. But okay.
Oh, right. Do they have? I've never been there either. But have they got multiple facilities there, or is there just one?
St. Anthony Falls is a multiple level facility. So when they've got different experimental basins. They've also got an outdoor stream lab, which once again takes the water of the Mississippi, runs it through an outdoor stream, puts it back in. The sort of mother of all North American experimental basins is Jurassic Tank, what we lovingly call Jurassic Tank, which is the only basin, I think, in North America with variable subsidence. So a lot of people have gone simple, where it's either piston-like subsidence or hinge-like subsidence. But Jurassic Tank can do variable subsidence.
Where they have multiple pistons across the tank?
No, it's a weird system of I think it's a polygonal system of essentially draining gravel at different rates.
I see.
And so you can get all sorts. You can build your own complex fault system. You can have forward tilted basins, backward tilted basins, but also any combination of subsidence patterns that you choose to deal with, which is beautiful in theory. It's also a bear to manage. So which is why we have one of those. Usually, rather than, I think, the facilities and the types of experiments being run, an important frontier for us is actually talking to each other. So good communication between the physical experimentalists and, say, numerical modelists, the people who are you guys familiar with CSDMS based in Boulder? A whole bunch of landscape models are essentially housed within their system. They have in-house coders who try to get different models to talk to each other. And so that's kind of our central go-to place. If we're looking for a model to do a specific problem, we pick up someone's model from there and try to tweak it for our needs and, feed it back into the system. Experimentalists, possibly because the discipline is fairly young, we have not done a very good job of talking to each other. And so now we're getting to the stage where there is enough of us that we need to make sure, one, we're just not repeating someone else's experiment, because why would you do that? That's just crazy. You should run a new experiment and use someone else's data, which then means that people have to share the data. It has to be very well documented. So the metadata and everything has to be managed really well. And finally, actually making it universally available to people who aren't really that interested in running experiments so much as using experimental data, whether it's a landscape modeler or someone in the oil industry or someone like me who, if I can avoid it, I don't run my own experiment. I'd rather use someone else's data, because that way you're not wasting a bunch of time. Because some of these experiments literally take years.
Yeah, I bet. Yeah.
So I think that's a frontier that has become quite important in recent years. But yeah, there's plenty of new kinds of experiments that can be run. There always are. Do you have a specific idea of
well, I guess I was wondering
I'm
if
just
there's
thinking, oh my gosh, all the experiments, all the data. So
if there's like an equivalent of a kind of Mars shot going on in the kind of you know, what would you call it, stratigraphy, soft rock geology, world of experimentation and data collection. But I feel like if there isn't, then an awesome surrogate Mars shot, and it's probably as difficult to achieve as you just alluded to it, is getting good at open data. And because I suspect that there's a Mars worth, sorry, I don't know why I'm picking on Mars, but there's just a gigantic pool of kind of semi-usable data out there. Some of it probably highly usable, some of it probably too far gone. And I worry, I mean, it's bad enough industry being like that, but I mean, when you look at academia, a lot of it's publicly funded research. I mean, it should be open, and eventually it's going to be unrecoverable because the people involved will be gone and so on and so forth. So if there isn't a Mars shot going on, then let's make it that. And how big a mountain is that to climb? Mixing a lot of metaphors.
That's a very big pile of sand to climb. So I mean, we and I say we as the royal we. I wasn't really leading the charge on this. But we as a community have begun to start, just archiving data a little bit better. One of the great incentives for academics, right, is credit. And so, a lot of people in the past have been able to release their field data sets with DOIs, but there wasn't really an avenue for an experimentalist to do that. So that, this way, even say negative results potentially might be used down the line. But now you have an incentive for an academic to collate the data, make sure that the data has good hygiene, is readable, and people can deal with it. So well taken care of and published with the DOI. That way they cite you, and at least your work is acknowledged. And so that's happening now. A not insignificant problem associated with some of the experiments that I just described to you is just the sheer volume of data. So, for instance, any one long-term experiment usually will have, photographs collected high temporal resolution. Likely, there's going to be high-resolution video. If you're collecting DEMs, you're talking massive amounts of data because this is at the scale of like every millimeter or so in a grid that's really high resolution. And then if you've got like flow data, sediment transport data, velocity profiles, this is a lot of data. And so ultimately what it comes down to is who's going to house that and how much space do we need, because that space is obviously going to grow exponentially. And so that's, I think, where eventually we're going to hit our sticking point. Right now we have what's called the seed data network, where a lot of data is stored with digital object identifiers, which is great. A lot of the metadata is sort of QC'd, so it's easy to sort of locate different data sets, but also there's some sort of a standardized format for people describing how the data was collected and how it was processed and so on. But eventually, yes, we're probably going to run into an issue where we just don't have enough space to store it, and so I guess we'll deal with that when it happens. We're not quite there. We're almost there, though.
Yeah. I mean, I guess the data is already being stored. Do you know what I mean? Like, it's just that it's
how it's stored. Yeah.
Invisible because it's it's on laptops and corners of servers and things.
Or in individual
I mean,
library databases and different universities maybe, or as in my case for many years, is multiple terabyte hard drives, which is the worst way to store data that took months to collect.
Yeah. I mean, but definitely some disciplines seem to have like sorted it out. Like it seems like the global seismologists have really. I mean, I know their data is relatively homogeneous, like it's all basically just, seismic traces.
Yeah.
So that makes things a lot easier. But I think one thing that it's easy to kind of forget as a motivating factor is just if your data is easy for other people to use, then it's also easy for you to use.
Yeah.
And I feel like a lot of people sort of just struggle along with kind of broken databases, and actually, and this is, I think, should be a big motivator for governments, especially. It's just like, well, if you solve the problem of making it publicly available, now it's also available to you and to your stakeholders, and to you've actually killed multiple birds with one stone. Oh man, I must stop with the metaphors and similes. But yeah, cool. I mean, it's interesting. There's would you say your sort of main affiliate professional society, would that be AGU?
AGU, GSA, AAPG. The first two of late have become more important to me than AAPG.
Yeah, it just like AGU, I would say, seem to be getting their act together digitally, and or have, they're well into that, and so that gives me encouragement that I bet there would be substantial, well, I want to say financial support, but I mean there would be they'd be very receptive to helping to figure out the solution to that problem.
Well, that's part of it. They're also JGR, Journal of Geophysical Research, Earth Surface, which is what I would normally publish in. They require that your data be publicly available now. So, which is great. Yeah. Which also means that part of the wrap up for any project is not just the submission, but having your students tidy up the data so you can use it, which is great.
Yeah, and how long does that take generally? I mean, it must take quite a while.
It depends on how you set out. I have learned the hard way, as I was not very organized as a PhD student. I quickly got very organized as a postdoc because just it just follows you around after that, just like terabytes of unorganized data. But yeah, so I think it's actually really straightforward if you start out knowing where you're headed. So have the right folders, have the right organization, all the prompts in place to make your checklist of things that need to be filled out, probably at the end of every day, if not at the end of the experiment. At the end of it all, I mean, you write a paragraph to introduce your data and where it's going, and then that's it. You upload it.
Is there any or much proprietary software floating around in your space?
Yes, some, I would say. For instance, and this is a hard one because it actually does fund St. Anthony Falls, but like some of the laser mapping systems that we have were developed at St. Anthony Falls, and so it's not just a laser mapping system, but it's like a whole circuit board of computer managed inputs, like your sediment flux, your water flux.
Okay, right.
Sea level changes, when you when you send the system out to map the surface and things like that. I would say that's proprietary. It's expensive, so it's like tenure track startup package expensive, or not. The less said about that, the better. So that's proprietary. A lot of measurement systems. So, for instance, if you're measuring flow velocities and things like that, usually there's going to be some interface for which you're paying for. You're paying for it when you buy the instrument, whether you're measuring flow velocities or whatever it is. And that would be the kind of proprietary software that I have in mind. Other than that, we're getting there because a lot of people are now using Python, so we don't have to deal with MATLAB anymore. I still haven't learned Python to my shame. I'm still holding on to MATLAB with a death grip. I know, but the problem is I'm always so crunched for time, right? And then I was like,
Totally.
I already know how to do it all in MATLAB. But I've been telling my students to start learning Python. There's QGIS, so you don't have to deal with ArcGIS anymore. Our seismic interpretation, Kingdom Suite, they're not as good as the landmark systems, or I shouldn't say that, should I? I probably shouldn't say this. This sounds like an endorsement of some sort. But there's enough.
That's right, Landmark, if you're listening, we'll take a big check.
There's enough enough software that will give you an academic license, a free license.
Sure.
But yeah, there could be more. There can always be more.
Well, folks, we've reached that point of the show that I'm very excited about this show, by the way, where we talk about what we're reading. And I'm just going to kick us off here by saying that I am between books right now. And before you guys tell me what you're reading, I want to ask Matt, should I get a copy of Algorithms Illuminated? Was it worth it?
Oh, yeah. I would say that it is. If you're quite, the first volume, because I think there are going to be 5 or something, if I remember rightly, is all on algorithm analysis and Big O. So, if that interests you, I would go for it. It's certainly much more accessible than, say, Knuth.
Well,
which is
I'm looking for
hard to read.
Yes, indeed. I did enough of that in school. I could go for something that's a fun, light read, which is what everybody's been saying about that book. So,
yeah, and the other fun computer science book that I read last year that I did enjoy was Computer Science Distilled, that we talked about on the show a while back. And that's a little bit too cursory, right? It's like a half-hour read, whereas this is a bit more involved, and it's actually got exercises. It's a course, right? It's come from a course at Stanford, so it's got quizzes and all sorts.
Cool.
Yeah.
So what are you reading right now?
I knew you were going to say that because I still haven't looked up the name of the book that I'm reading. Anjali, what are you reading?
You can pass.
So, when you guys said that you were going to ask me what I was reading, I couldn't figure out whether you were going to ask me about what I'm reading scientifically, which sounded so boring.
No way.
Or actually reading for fun.
Comic books.
I have, oh my goodness, now for the longest time, I've been reading the biography of Cleopatra written by Stacy Schiff. This came out many years ago. I began it many years ago, but I picked it up over the winter holiday again, determined to finish it, and I still haven't finished it. But yeah, it's a biography of a historical female, this time written by a woman, and you'd be surprised how different the female biographer's take on Cleopatra is.
Have you read another biography of Cleopatra written by a man?
Well, we kind of know. No, I haven't. It's a short answer, but we kind of know that Cicero, for instance, talked a lot about Cleopatra, and mostly he was just agonizing over how horrible he thought she was and how bad she was for Rome. He was also, by all accounts, a pretty grumpy old man. But yeah, you'd be surprised, right? It's the loudest voices and often who are often also the worst critics that have been recorded in history. And so it's a nice book to read.
Awesome.
When I am reading
it. Well, we hope to hear back soon about how the end goes. Matt, did you find your book?
It's one thing I didn't realize when I bought. I can't remember where I picked it up. I think I picked it up in a secondhand bookstore, and I didn't realize when I bought it that it was as old as it is. I think it came out in 2000. So it's probably out of print, and that's my excuse for why I can't figure out what on earth the book was called, because he's talking about like the '98 Winter Olympics. So Winter Olympics are starting soon, aren't they? Pretty excited about that.
Yes, they are. Hey, Matt, what's your favorite Winter Olympic sport?
Cross-country skiing. It's a no-brainer. Biathlon's kind of cool, but I don't really get the shooting side, so I just like the skiing.
Cool. Anjali, thanks for joining us.
Yeah, thanks for having me. It was fun.
Yeah, thank you. It's nice talking to you.
We'll see you next week. Undersampled Radio, episode 70. Bye.
Bye.